Welcome to AP Podcast 12.7. This is on collision theory. Now, this whole chapter we've been talking about reaction rates and reaction mechanisms and things like that. And what we're going to talk about now is really why these reactions are taking place. And it all has to do with this collision theory. And in order to understand exactly what's going on, we have to remember that for a reaction to occur, you've got to have three different things happening. One, the molecules have to bump into each other. All right, so they've got to bump into each other in order to react. We don't really think about that. If you think about all our experiments we've done, we take some chemicals, we mix them together, and then it just magic happens. We get flame, we get bubbles, we get precipitates. But what's going on the molecular level is that the molecules are actually bumping into each other. Now, besides bumping into each other, because you can imagine in a vessel where I've got some gases just flowing around, maybe I've got oxygen and hydrogen gas bouncing around, and they're bumping into each other, but nothing's happening. Well, because there's another factor that's involved, and that's they've got to bump into each other with enough energy. And this minimum energy we call the activation energy. Okay, activation energy is the minimum amount of energy to get a reaction to go. And you'll see this E sub ACT quite a bit to represent the activation energy. So let's say they're bumping into each other. They're bumping into each other with enough energy, but there's still one more factor, and that's the fact that the molecules have to have the correct orientation. So let's say I have a molecule that looks like this, some simple Richardson drawing here, and I have another molecule that looks like this, and it's a 3-atom molecule, and they bump into each other this way, and nothing happens. But it turns out that if you can get them to bump in this way, kind of perpendicular to each other, and I'm making this really simplified, so just understand that. So if they bump into each other perpendicularly, then maybe we get some kind of new molecule. Who knows? Okay, but something like that. So those three factors have to occur. Now, if those three things don't happen, then what you get is no reaction. So even though with our big clunky eyes we're just looking at things reacting, we don't really think about the microscopic level, and that's what collision theory tells us. Now, this activation energy that I was talking about in step 2, that minimum amount of energy, there's a lot of really good demos and visuals for this, but one that I like the best is a bicycle. Guy's on a bicycle, and here's Mr. Stickman, and here's my awesome Richardson drawing, and he's trying to go up the hill, right? And the only way he can get to this side to go down is if he can get all the way up to the top. Well, the activation energy is the minimum energy that it takes to get to this top part. And so we can have all our reactants having a certain amount of energy, let's say down in here, and nothing happens. If you can get them to have enough energy to get up there, and how do we do that, by the way? Well, think of all the reactions we've done. Maybe we've added some kind of spark. Remember the rocket lab. We added a spark to get that reaction go. But you've got to add something to get them to go. And so this activation energy I'm going to talk about a lot. It's this hump, this minimum energy to get the molecules to go before you can get down to the product side. All right, and this is just energy. So you can see, look, the reactants is up here, the products are down there. The change in energy, right, would be the difference right there. Okay, so that would be the change in energy, and this is going to obviously be an exothermic reaction because our products are going to be at a lower energy state, right? All right, so let's talk about the factors that are involved in the rate of reaction. The concentration is one of the main ones. Obviously, if you take a beaker, okay, if I've got a beaker, and we'll make this really simple. Let's say I have a beaker and I've got 4 molecules in it, all right? And I've got another beaker and I've got 10 molecules in it. Okay, same volume. This one is more concentrated, right? More concentrated. Well, let's say we give them, they have the same temperature, they have the same amount of kinetic energy, they're bumping into each other, they're bumping into each other with enough force. This one right here, because you have a greater concentration, is going to increase the odds of a collision taking place. It just makes sense. 10 things would bump into each other more often than just 4 things. And if we do this with a pressure, and we've got, these are gases, what happens when I increase the pressure? What am I doing? Remember our piston diagram? I'm decreasing the volume. So now I've got all these molecules in here bumping into each other in this small space, and that's going to also definitely do the same thing. So if you increase the concentration, or with gases you increase the pressure, that will increase the reaction rate. What's another major factor? If you had to guess, you'd probably guess this, and that's the temperature. Now Arrhenius, and that's a guy who came up with a bunch of ideas about collision theory, but basically he said that the reaction rate should increase if you increase the temperature. Now think about it. What happens to molecules as we heat up a substance? They're going to start moving faster. They've got greater kinetic energy, and so that kinetic energy is going to cause them to bump into each other more often. They're going to bump into each other with a sufficient amount of energy and most likely the right orientation. And so you get the number of collisions increases, and so therefore you'll get a greater rate of reaction. And this part right here, this is kind of important to note right here, that that number of collisions, when it happens, when you heat it up, it goes up exponentially. So it's not like it just starts to increase. I mean, it really increases. All right. So here's a nice little diagram. Now look at this, shows you basically how the activation energy and the temperature are related. Over here on this side we've got the number of particles right here, and then over here we've got the energy. So energy is increasing as we go this way. Now if I'm talking about some molecules at a lower temperature, here's the activation energy hub. Look at how many of those molecules have enough energy to get it to go. Not very many, right? Conversely, though, if I look at something that's high in temperature, look how many more molecules have enough energy to overcome that hump. So you increase the temperature, you increase the number of molecules that have the activation energy, and then the reaction rate is going to increase. So there's two main factors. We've got concentration and temperature, and then the last one is a big one, and they really focus on this in AP, and that is a catalyst. And you probably know what a catalyst is from biology, but it's simply a chemical that speeds up a reaction and is not part of the reaction. So when you're all done with the reaction, you still have it. Something that we have in our bodies that we use all the time are enzymes, and those are the catalysts that allow our body to do complex reactions at a temperature that's not going to burn us up. All right. But the neat thing about catalysts is that that hump is still the same. I mean, you still are going to use the same amount of energy, but you get a new pathway, or what the College Board prefers as an alternative pathway, when you use a catalyst. So let me show you a visual of the new pathway. And I can tell you this right now. This is a drawing you have to be able to make. Whether it's a test for me or if it's a test for the College Board, it's super important. So here's our good old drawing with, the amount of energy it's going to take. Way up here is our activation energy. So from here to here is the amount of activation energy it's going to take. Sorry, I can't draw a straight line. Let's try it better. Oh, there we go. From there to there is how much activation energy it's going to take. And with a catalyst, here's a new pathway. And so notice this hump. This hump is much smaller. So the amount of activation energy it's going to take with a catalyst is way smaller. And that's an advantage. So what that's going to do is more molecules are going to be able to achieve that peak, and therefore you'll get a quicker reaction. The important thing, though, is notice that this point right here and this point right here does not change dependent upon how high the hump is. In other words, the amount of enthalpy it's going to take, the energy it's going to take to do this reaction, or not do this reaction, in this case, the amount of energy that's given off is still going to be the same regardless of whether you use a catalyst or not. But this lower activation energy is going to help us do it. So this alternative pathway, this new pathway, and you really got to be able to draw that because they look for that all the time. And so here's another graph that just kind of shows the number of particles. Here we are without a catalyst. This small, look at this, we only have a relatively small number of molecules that can actually get there. But now if we go with a catalyst, now we have this whole area. So you have way more molecules that can achieve that, and therefore a catalyst helps that reaction go real go faster. So real important stuff. Catalysts, also the temperature and the concentration all affect reaction rate. And that's it for chapter 12. So if you have any questions, we'll talk about it later. See ya.